All right, we'll do part A together. Okay, once we do these 10, then we will finish. Okay, we'll fill out this form in our lab handout. All right, set A, and our first one here is CS2. Okay, CS2. This is called carbon disulfide. Carbon disulfide. Okay, so. And let's go ahead and start that. Let me just get some pens here and pencils. Mess. All right, carbon disulfide is our first one. Okay, everyone see this? So what's our central atom? Carbon. What is carbon happy at? No. What's carbon happy at?
Carbon is happy at 6. 4.
Okay.
4.
Just randomly guessing numbers. Okay. So 1, 2, 3, 4. Okay, carbon loves 4 actually. Okay, carbon loves 4. All right. All right. So how will we get carbon and the two sulfurs together if carbon loves 4?
Double bond.
Okay, so we'll have a double bond with sulfur. Okay, and a double bond with sulfur. Okay, what about the electrons on the sulfur? Carbon is happy at 4. What is sulfur happy at? It's below oxygen. Okay, it's below oxygen, so what is oxygen happy at? 6. Okay, but how many do we have? 2. Okay, so we need a total of 16 valence electrons. Okay, so we have 1, 2, 3, 4, 5, 6, 7, 8. Where will 9, 10, 11, 12, 13, 14, 15, 16 go? Where will they go? 1, 2, 3, 4, 5, 6, 7, 8. Okay, 9, 10, 11, 12, 13, 14, 15, 16. Okay. You're in my lecture, so you can just follow along and it will make sense to you when I go over this. So I don't expect you to know this. Okay, so just write it down. Actually, that helps. That'll help you because this lab will be done. Okay, so, yeah. All right. So let's do formal charge and.
Is it important that on the right it's on the right and the top, and on the left it's on the top and the bottom, or is that?
No, it doesn't matter where these lone pairs go, as long as it's around the sulfur. All right. So. Octet rule, 1, 2, 3, 4, 5, 6, 7, 8. Is that sulfur happy?
Yes.
Okay, what about the formal charge for that sulfur? 1, 2, 3, 4, 5, 6. What is sulfur happy at? 6. What's 6 minus 6? 0. So this is 0, this is 0. What about this carbon? 1, 2, 3, 4. What is carbon happy at? 4. What's 4 minus 4? 0. Okay, the octet rule. 1, 2, 3, 4, 5, 6, 7, 8. Okay. So central atom. Okay, Elizabeth, this is central atom. Okay, how many bonding and how many non-bonding?
4 bonding, 2 non-bonding.
2 bonding and how many lone pairs?
4.
2 bonding and how many lone pairs on the central atom?
0.
0. Okay, so what's 2 bonding and 0 lone pairs? Do you have that sheet? You got it. Good. 2 bonding, 0 lone pair. Linear. Okay, so the molecular geometry and the electron pair geometry is linear. linear. Okay, you can look that up on that sheet that I handed out. I gave you guys. Okay, linear. All right, so something that's a straight line, it's just a straight line. There's no 3D. Is there a 3D aspect to a line? It-
No.
Is something pointing towards you or something pointing back? No. Okay. What's the central atom hybridization for 2, 0? What's 2 plus 0? 2. So it's going to take how much from S? You can only take 1 from S because there's only one slot. And how many from P? 1 from S, and then how much to get to 2? 1 S, and then how many P?
2.
So this is SP2. Okay. SP3, that would be 4. SP2 would be 3. So what would it be? Huh?
S2.
Well, S only has 1.
Okay, so S1P1?
Right, SP1. Very good. Well, we don't say 1. SP. SP. So it's an SP hybridized carbon. Okay. Okay, very good. Okay. Okay, one from the S orbital and one from the P orbital. Okay, that gives us the 2. Okay, so this is an SP hybridized carbon. All right, so I didn't go over polarity, but I'll go over it in lecture. So this sulfur is electronegative. Okay, so it pulls. Okay, it's going to pull this side, making it partial negative. That is the Greek symbol delta, which means negative. Okay, the same thing is this sulfur. It's going to do it on the other side also. Okay, partial negative. Okay, so this pull from this sulfur, which is electronegative, it pulls to the left. This sulfur, its pull, the electronegative, pulls to the right. Okay, this is partial negative, and this is partial negative. Okay, we put a little arrow with a tail, which means it's pulling. Partial negative on one end, partial negative on this end. So this molecule has a partial negative end here, but I want to convince you is that this partial negative here pull is canceled by what? Okay, the pull on the other end. So this is pulling that way, this bond is pulling that way from that sulfur, and that sulfur is pulling this way. Okay, this pull cancels out that pull. Okay, when they cancel each other out like that, we call it nonpolar. Okay, so the polarity can be one of two things. It could be polar or nonpolar. Okay, but this is nonpolar because the poles cancel each other out. Okay, see this sulfur pull on the left is canceled straight by the sulfur pull on the right. Okay, so it makes it nonpolar. If they didn't cancel, if there's any partial positive left over, partial negative left over, it would be polar. But this is not polar. It's nonpolar.
So what would H2O be if it's, since the poles are kind of like downward?
That would definitely be polar. Okay, most definitely. All right, so we finished this one. It's a linear molecule. Okay, CS2. Okay, let's do our second one here. Okay, this would be number 2. AlCl3. Okay, AlCl3 is this one. Get this straight here. All right, AlCl3. Okay. Okay, this is called this is called aluminum trichloride, I believe. All right, so what is Al happy at?
3.
Okay, Al is happy at 3. Okay, what is Cl happy at? 7, but we have 3 of them, so we have a total of 24 valence electrons. Okay, so we'll make aluminum our central atom. Okay. Okay, and we will have a Cl here, a Cl, and a Cl. Okay, aluminum loves 3. Okay, so 1, 2, 3, 4, 5, 6. Let's fill out the rest. Okay, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24. Okay. And that would be what AlCl3 is. Okay. Let's do formal charge and octet rule. Let's first do aluminum. Okay, Al first. 1, 2, 3. What is Al happy at? 3. What's 3 minus 3?
0.
Good. So 0 formal charge. Okay, what about this Cl? Okay, 1, 2. Let's do octet rule for Al. 1, 2, 3, 4, 5, 6. Okay, is that okay for aluminum? Yes. Okay, the octet rule has a lot of exceptions. Okay, let's do Cl here. Okay, Cl is 1, 2, 3, 4, 5, 6, 7, 8. Is that octet satisfied? Okay, and what about the formal charge here? Okay, 1, 2, 3, 4, 5, 6, 7. 7. What is Cl happy at? 7. What's 7 minus 7?
0.
That's formal charge on this Cl, that Cl, and that Cl is 0. All right, how many bonding and how many lone pairs? I think you're good at this. Can you tell me, Liz, how many bonding?
The lone pairs is 3 and 0.
3 bonding and how many lone pairs?
0.
0. So what's 3 and 0?
It's bent. It's a bent molecular geometry.
3 bonds, 0 lone pairs. 3 bonds, 0 lone pairs. Trigonal planar. Okay, so
What?
trigonal planar. So this is the one that we kind of went over in lecture. It has a perfect bond angle of 120 degrees. Okay, 3 bonds, 0 lone pairs. Okay, 3 bonds, 0 lone pairs. Okay, this would be nice and perfect at 120 degrees. Okay, and as you guys stated correctly, this would be 180 degrees because it's a straight line. Okay, we can also put in our lone pairs if we want to here. So all right, hybridization. Okay, how will we get to 3? This is an sp2 hybridized aluminum. Very good. Okay, electron pair geometry. Because there are no lone pairs, if there's lone pairs, things get distorted. Okay, that was the theme in this lecture this morning. If there are lone pairs, things get distorted. If there's no lone pairs, they're the same. So this is trigonal planar. And this is trigonal planar. Okay, polarity. Okay, so is this polar or non-polar? Okay, it's tricky.
It's not polar, but it's pulling on also.
And they cancel each other out. So this pull at an angle and this pull at an angle. This Cl is pulling up top. So I want you to look. Let's see here. If this pull at an angle is pulling this way and this pull Cl is pulling that way, what is the sum? Okay, the sum actually is pulling down. Everyone see this? The sum in red pulls down, which cancels out the pulling up here. Okay, so if you add this angle, if you add this angle with this angle, if you add those two vectors, you know vectors, or maybe not, you'll learn it in physics. Okay, the sum is in the red. This red, which is the addition of these two green, cancels out the one fully going up. So because this down cancels out this up, this is also nonpolar. Okay, it's kind of tricky, but this is the answer. That Cl is electronegative. Okay, but these two at an angle sum to one that's going down, which cancels the one going straight up. All right, so that is aluminum trichloride. Okay. All right, let's do number 3 here. We got 8 more of these to go. Okay, SiH4. Okay, what is silicon happy at? It's right below carbon. 4, what is hydrogen happy at?
1.
Okay, but we have 4 of those. Okay, so we need to get 8 valence electrons around silicon, whatever you call that's called, silicon trihydride, or yes? Tetrahydride, tetra. So how will we draw this? Okay, a silicon with 4 H's around it. Okay. All right, let's do the octet rule. 1, 2, 3, 4, 5, 6, 7, 8. What about the formal charge? 1, 2, 3, 4. What is silicon happy at? 4. What's 4 minus 4? 0. Hydrogen, 1, 2. Is that good? For the octet, hydrogen is good. Okay, formal charge, 1. 1. Okay, what is hydrogen happy at? 1. What's 1 minus 1? 0. Very good. All right. How many bonding and how many lone pairs? 4 bonds, 0 lone pairs. So what's 4 bonds, 0 lone pairs? Okay. Tetrahedral. Do you know how to draw a tetrahedron? We did it in class. Okay, so just as you did for CH4, you'll do the exact same thing here. Okay. So this is the tetrahedron. Okay. Nice angles of 109.5 degrees. 109.5 degrees. Okay. Exactly the same as this morning's lecture, CH4. Exactly the same. Okay. All right, what hybridization is this? 4 and 0.
S1P3.
We just say sp3. Okay, don't say 1, just say sp3. Okay, but that's the right answer. Okay, sp3. Generally, they don't say 1. They don't say S1, P1. They just say S and P. The same as CH4 we did in class. This is an sp3 hybridized silicon. All right, because there's no lone pair, if there's a lone pair, there's distortion. But there's no lone pair, so you can just go with the electron pair geometry and the molecular geometry being the same, and that's tetrahedral. Okay, is this polar or non-polar? Okay, hydrogen is very weak. Hydrogen cannot pull. Okay, most of the electronegative elements are here. Okay, these guys are like vacuum cleaners. They are sucking up electron density. Okay, hydrogen doesn't do much of that. Hydrogen doesn't pull, so this would be non-polar. Okay, if there's a fluorine there, chlorine, oxygen, then yeah, I would say there's a lot of pulling. Okay, it pulls on that bond. Hydrogen as the outer atom does not really pull, so this would be non-polar. Okay, so onward we move to our next one here. What is our next one? Okay, all right. H3O plus. H3O plus. Okay, very interesting. Not H2O, but H3O plus. What is this all about? This is number 4. All right, so what is hydrogen happy at? 1, but we got 3 of those. What is oxygen happy at?
6.
6. And what does that plus mean?
It's losing.
Very good. It's lost an electron. So we got to get 8 valence electrons around hydromonium or H3O plus. So how will we do that? Okay. What will be our central atom? Okay, hydrogen, hydrogen, hydrogen. Okay. So 1, 2, 3, 4, 5, 6. Where will 7 and 8 go? Where will it go? Okay, we got 1, 2, 3, 4, 5, 6, but we need 8. So where will electrons 7 and 8?
On the dots above it.
On where?
Above it, put the dot.
On what atom?
The oxygen.
Right. Okay, on the oxygen. Okay, so let's do formal charge. Let's do this hydrogen. 1. What is hydrogen happy at? 1. What's 1 minus 1? 0. Okay, octet rule. 1, 2. That's perfectly fine for hydrogen. Okay, this oxygen. Let's do this oxygen together. Let's do octet for this oxygen. 1, 2, 3, 4, 5, 6, 7, and 8. Okay, the octet rule is satisfied. What about the formal charge? Okay, everyone count with me. Ready? 1, 2, 3, 4, 5. What is oxygen happy at?
6.
6 minus 5. The plus 1 goes here. Okay. That's where the plus 1 goes. Okay. So how many bonding and how many lone pairs? 3 bonding and 1 lone pair. Okay, so what will that be?
It's a molecular event, but
So you on that one sheet you're going to do 3 bonding and 1 lone pair. So you're going to do 4 and 1. What's 4 and 1? 4 bonding, 1 of them is lone pair. Let me see that, Daniela. 4 bonding, 1 lone pairs.
Oh, so
It will be trigonal pyramidal.
trigonal?
Yeah, 4 bonding, and out of those 4, 1 is a lone pair. So it's going to be trigonal pyramidal. Okay. You can actually see in the trigonal pyramidal. Okay, here's your hydrogen, 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 and there's your lone pair. Okay, so we got 4 bonding, 1 lone pair. Out of the 4, 1 of them is a lone pair. So what is the geometry? Trigonal pyramidal. Okay, trigonal pyramidal. I may use this for later on, so I'll. All right, so let's sketch a trigonal pyramidal. We're going to sketch it just like this. Okay, we'll sketch it just like this. Okay, so we have 1 coming out, 1 coming out, 1 going back, and then a lone pair. Okay, so So I'm going to do it exactly like this, except they'll have a lone pair substituting. Okay. And usually when we have a lone pair, we'll put it in a lobe like this. Okay, and don't forget this has a positive charge. Okay. So it's just like this one above, except I removed the hydrogen and filled it in with an electron. Okay, took this one, removed it, and put in an electron there. It's exactly like this one, except we removed one of those outer atoms and replaced it with this electron that's sticking in this lobe. All right, so that is H3O plus. Okay, 3 bonding, 1 lone pair. What's the hybridization? What's 3 plus 1? 4. So how will we get 4? Okay, it's going to be the same thing as above, okay? It's going to be an sp3 hybridized oxygen. Okay, so 3, 1. One of those lone pairs is going to occupy one of the orbitals. Okay, what is the electron pair geometry? Okay, the electron pair geometry, when you have 4, is tetrahedral. Everyone look at me. The electron pair geometry, when you have 4, is tetrahedral. Okay, but when you have 1 lone pair out of those 4, what is it? It's trigonal pyramidal. Okay, so the electron pair geometry is going to be tetrahedral, just like above, but the lone pair makes it trigonal pyramidal. So the electron pair geometry in this column is tetrahedral, just like above. But the molecular geometry is trigonal pyramidal. Now, why is it trigonal pyramidal? Because of the what? That lone pair makes this from tetrahedral to trigonal pyramidal. Very good job, Daniela. All right, is this polar or non-polar? Okay, he's polar. First of all, there's no symmetry. There's that electron sticking out like a sore thumb. This is definitely polar, okay? Okay, this is a polar molecule. All right, that is number 4. We got 6 more of these to go, then we'll finish set A, and then we'll be finished with the lab. This pre-lab and post-lab is something I'll have to go over with in lecture, okay? Definitely sigma bonds and pi bonds I have not gone over. All right, what's number 5 here? Xenon tetrafluoride. Okay, xenon tetrafluoride. This sounds complicated. Let's check it out. Okay, we're on number 5 here. Xenon tetrafluoride. Okay, what is xenon happy at? 8. Very good. What is fluorine happy at? 7, but we have 4 of those, so it's 28. So we need to get 36 valence electrons around XeF4. What will our central atom be? Xenon, and then how many fluorines? Fluorine, okay. There won't be a double bond with halogens. Okay, that will mess up the formal charge a lot. Okay, so no double bonds with halogens. Okay, so let's count with me. 1, 2, 3, 4, 5, 6, 7, 8. Okay, let's go. Everyone do this with me. Okay, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30, 31, 32. Okay, where will 33, 34, and 35, and 36 go? On what atom? Yes. Okay. So 33, 34, 35, and 36 will go there. Okay. Okay, let's do the formal charge and octet rule. Okay, let's do it for the xenon here. Okay, octet 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. 9, 10, 11, 12. This is called an expanded octet, okay, which is fine. Okay, the formal charge is something I'd like for you guys to do with me. Okay, ready? Count with me. 1, 2, 3, 4, 5, 6, 7, 8. What is xenon happy at? 8. What's 8 minus 8? 0. So this has a 0 formal charge. What about this fluorine? We'll just do one fluorine, okay? 1, 2, 3, 4, 5, 6, 7, 8. Octet satisfied. Let's do formal charge. Okay, everyone count with me. Ready? 1, 2, 3, 4, 5, 6, 7. What is fluorine happy at? 7. What's 7 minus 7? 0. So 0 across the board. 0 for xenon. This whole thing is a 0 charge. So how many bonding things are around the xenon? 4 fluorines and 2 lone pairs, right? So this is 4 bonds and how many lone pairs? 2. So what's 4 bonds and how many lone pairs? Okay. So we have 6, and out of those 6, how many? Put this back up here. Okay, out of those 6, how many are lone pairs? 2. Square planar. Square planar. Okay. So we'll do a square planar just like they guided us here. Okay. Just like we guided us here. Actually, we can make it there. We'll do it in lecture. We won't do that in lab. Okay. Square planar. Okay. Square. Okay. So okay, we have I'll have one lone pair go up. Okay, another lone pair go down. Okay, I'll have one of the fluorines come out above towards you guys. I'll have another fluorine coming out away from you guys. Okay, I'm just following this. Okay, just substituting the lone pairs and the F's here. And then I'll have, okay, this is called a dash bond, this is called a wedge bond, and I'll have one fluorine go on the plane and another fluorine go on the plane. There's many ways to draw this, okay? Square planar. So remember, these lone pairs go in lobes. One of these is coming out towards you. This one in the dash is going back. This one is on the plane of the paper. One on the left, one on the right. Okay, so something like that you can draw. Okay. Again, this is on the plane of the paper. This is coming towards you. This is going back. This is on the plane of the paper going up. This is on the plane of the paper going down. Right, in lecture, I'll construct this and you'll get a better idea in lecture, so make sure you come to lecture on Wednesday. All right? You plan on coming, right?
Yeah.
You don't sound so enthusiastic about that. Okay, so square planar. What is the electron pair geometry for something that has 6 bonding? Out of those 6, 2 are lone pairs. What's the electron pair geometry? Yes, octahedral. But those 2 lone pairs don't make it octahedral. What will they make it? Square planar. Very good. Whoever said that. Was that you, Blake? Okay. 6 bonding. Okay, but out of those 6, 2 are lone pairs. So those 2 lone pairs distort the structure, making it square planar. Okay, I have pair and electron going up, one going towards you, one going behind you, one on the plane of the paper, one on the plane of the paper. All right, so the electron pair geometry is octahedral. And the molecular geometry is what, one more time? Okay, square planar. Okay, what's the central hybridization? Okay. 4 bonds, 2 lone pairs.
SP2.
There will be Ds, but how many? SPS is 1. How many are in Ps? Okay, so 1 slot for S, 3 for P, and how many are in Ds? Okay, so this is going to be SP3 correct, D2. Okay, it's going to take, in order to get 6 binding, 2 of which are lone pairs, it's going to take 1 from S, 3 from P, and then 2 from D, right? Yeah, SP3, D2, hybridized xenon. Yep, this is correct. Right, is this polar or nonpolar?
Non-polar.
Whoever said nonpolar is correct. Okay, do you see why it's nonpolar? Okay, it's nonpolar because of symmetry. Okay, you see this electron? It's pulling up towards itself. Okay, you see this electron? It's pulling down towards itself. They cancel. This electron on the left, it's pulling this way. Okay. Okay. And this electron on the right, it's pulling this way. The left and right cancel. This fluorine that's coming towards you, it's pulling this way, partial negative. This fluorine pulling behind you, it's pulling this way, they cancel. All the moments cancel. All the poles cancel. When all of them cancel, it becomes nonpolar. What if I replace this fluorine with like a hydrogen? Then it's polar because the fluorines pull and there's nothing to balance out this pole. So there's symmetry. Okay, all the fluorines cancel out each other. All the electrons cancel out with each other. Okay, this is nonpolar. If I replace the fluorine with another molecule, it loses the symmetry, and the electronegativity poles do not cancel with each other. So symmetries is the reason why this is nonpolar. Okay? If you ever take Chem 2, they talk a lot about this stuff, polar versus nonpolar. All right, so that is XeF4. Okay, it's nonpolar. All right, what's next on our list here? Number 6. We have 5 more to go. PCl5. Okay. All right, what is phosphorus happy at?
5.
Okay, what is chlorine happy at?
7.
Okay, but we have 5 of those. Okay, so we need to get 40. Okay, 40 valence electrons are on PCl5. Okay. All right, so what will our central atom be? Okay, phosphorus, and we'll get 5 chlorines around it. Okay. 40 valence electrons. All right, let's fill out the electrons. Okay, everyone count with me. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, everyone ready? 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28. 29, 30, 31, 32, 33, 34, 35, 36, 37, 38, 39, 40. Okay, there we go. Okay, let's do the formal charge on one of these chlorines, okay? 1, 2, 3, 4, 5, 6, 7. What is this chlorine happy at? 7. What's 7 minus 7? 0. Okay, what about this phosphorus? Okay, everyone. 1, 2, 3, 4, 5. Okay, what is phosphorus happy at? 5. What's 5 minus 5? 0. Okay. Okay, let's do the octet for this phosphorus. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. It's okay. It's called an expanded octet, and expanded octets are all right. Expanded octet. Okay, so how many bonds and how many lone pairs?
5 and
5 bonds and how many lone pairs? 0. So what's 5 and 0? Trigonal bipyramidal. That's correct. 5 bonding outer things, 0 lone pairs, so it's trigonal bipyramidal. Okay. And it's the same molecular geometry because there's no lone pairs. Okay, the lone pairs will distort. So trigonal bipyramidal. All right, and let's do a trigonal bipyramidal. So you see this? I'm going to draw it just like this. Okay. I'm going to have 3 of these on the plane, up, down, to the left. I'll have one come towards you and one come back. These are the 5. Okay, these are the 5 chlorines. Okay, so here's my P. I'll have one up, down on the Cl, a Cl going to the left, a Cl going towards you, that's dash, a Cl going behind, that's wedge. Okay, so that's one way I can draw this in 3D. Trigonal bipyramidal. Okay, this is dash. Okay, that's wedge. All right, what's the central atom hybridization for 5 and 0? sp3d. Yes, sp3p, sp3d hybridized phosphorus. Okay, is this polar or nonpolar? All right, this Cl pull up, the Cl pulls down. Okay, this Cl pulls diagonally, this Cl pulls diagonally, so what's the net? Okay, the net is this way, and this Cl is pulling to the left. Okay, so what I want to convince you is that all the Cl pulls cancel. Okay, this one diagonal and this one diagonal, sum up, this is the sum, to something that's pulling on the right. This Cl is pulling on the left. So this and this cancel, left and right cancel based on the sum. This up and down cancel. So is this polar or non-polar if everything cancels? Okay, if everything cancels, what will it be? Non-polar. Okay. All right, so we got 4 more of these to go. CHCl3. Okay. We have some of this in the lab. It's called methylene chloride. Okay, methylene chloride. chloride, CHCl3. How will we do this? Carbon loves, you know what carbon loves, right? How much? Okay, so carbon, they'll have 3 Cl's. It doesn't matter the order now. And then the H. Okay. Okay, we'll put 3 lone pairs around the halogen. Very good. All right. What's 4 bonds and 0 lone pair? Okay, so we'll draw a tetrahedral. This is just like we did in class. Okay. Okay, doesn't matter the order for now. Don't worry about it. This is just like what we did in class. And we have a very nice angle of 109.5 degrees. What's the central hybridization for something that's 4 and 0? This is an sp3 hybridized carbon. And what's the electron pair geometry and molecular geometry, since there's no lone pairs? Tetrahedral, good. Okay, is this polar or non-polar? Very good. This Cl is going to pull, this Cl is going to pull, this Cl is going to pull, but there's nothing pulling the hydrogen. The hydrogen is very weak. So this has a net movement. Okay, so partial negative, partial negative, partial negative. There's no counterbalance here from this very weak hydrogen. So the minute you substitute that hydrogen with a chlorine, it's non-polar. But we have that one hydrogen, which is very weak. The other Cl's pull. You're correct, Elizabeth. This is polar. All right, let's do number 8 here. Okay, 8, 9, and 10. We're almost home on the stretch here. All right, C2H4. All right, carbon loves 4, so how will we do this? This may be a little tricky, but how will you do? Carbon loves 4, but there's 2 carbons. And then you double bond the carbons. And then what?
And then you one each. Yes.
And then?
Other side, H.
Perfect. Okay, very good. Okay. Excellent job. Okay, so you can see here carbon loves 4. 1, 2, 3, 4. Hydrogen loves 1, 1. You know, hydrogen happy at 1. 1 minus 1 is 0, so hydrogen has no charge. Carbon loves 4. 1, 2, 3, 4. Carbon happy at 4. 4 minus 4 is 0. It's the same thing for this carbon. It's the same thing for this carbon. All right, so this is a planar molecule. Okay. I'm going to rotate this 90 degrees. Okay. Okay, what's the hybridization of this carbon? This carbon here. Let's say there's 2 carbons, 2 central atoms. What's the hybridization of this carbon? How many bonding and how many lone pairs?
4 and 1.
Where's the 1 lone pair?
Oh, no, you're right.
I mean, this is not an electron. This is this carbon. Let me do it here.
I was thinking about it.
Okay, what's this carbon? How many bonding and how many lone pairs? 1, 2, and then 3. So how many lone pairs? 0. So 3 bonding and 0 lone pairs. Okay, what about this carbon here?
Same.
Same. Okay, so what's what's 3 bonds and 0 lone pairs? Trigonal planar. Okay, it has 2 sp2 carbons. Okay, so we have we have an sp2 hybridized carbon. We actually have 2 of them. Everyone see where both of them are at? This one and this one.
We have to do that one separately? Like we have to do each carbon separately?
Yes, because it has 2 central atoms.
Okay.
Because of the double bond. All right, you guys agree this is trigonal planar? Okay, 3 bonds and 0 lone pairs for one carbon, 3 bonds for 0 and 0 lone pairs for the other carbon. This is trigonal planar. Okay, what's the bond angle for this? Do you remember in class? Okay, it's going to be 120 degrees. Okay, trigonal planar, 120 degrees. Is this polar or non-polar? There's hydrogens here. Non-polar. Okay. All right, 9 and 10, and then we're finished. What's number 9 here? Okay, C2H3Cl3. Okay, let's finish that up. C2CH3Cl3. How many central atoms do you think this one will have? Okay, C2H3Cl3. How many central atoms? If you were to guess. C2H3Cl3. 2? Is that what you said? That's correct. Okay, 2 central carbons. C2H3Cl3. Okay, how will you do this? The 2 carbons will be in the middle. Then what?
Double bonded? Oh no?
H3Cl3. So, how would you do that? H3Cl3. Where would the H3 H's go? Where will the 3 Cl's go? Huh? You got this carbon with the carbon, that's correct. Where will the 3 H's go? Go ahead, answer it. Here's 1 H. Where would another H go? Okay, we could have an H go on this carbon. That's fine. Okay. What about a Cl?
Oh, on the rest of the sides that are left carbon.
I was just about to ask that.
Okay, that's one way of drawing it. Okay.
I felt like it was a trick question. So.
Those are called isomers because you can also there's something called isomers. You can also draw it like this. So there's really many ways to draw it. Okay, but it doesn't matter the order for this at this level. Okay. So or you could draw it like this, or you can draw it in any way around those 2 carbons. Okay. As long as you get the 3 Cl's and the 3 H's in there, right? Okay. Yeah. All right, we have, let's do 2, there's 2 central carbons here. Okay, carbon 1. What was carbon 1? Okay. How many bonds and how many lone pairs? It will have 4 bonds and 0 lone pairs. And what about the second carbon? How many bonds and how many lone pairs? No, I'm talking about this carbon here. How many bonding and how many lone pairs on carbon number?
Okay, so it's like separated. 40.
Very good. And what about carbon number 2?
40.
40. Okay, 40. Okay, so what is 40?
40 is tetrahedral.
Yeah, so these are two tetrahedrals joined together. Okay, these are two tetrahedrals joined together. So, okay, so this is one way to draw it. There's many ways to draw this, so. Okay. The idea is that you're getting two tetrahedrons coming together. Okay. Okay, one coming out, one on the plane of the paper. One at a 109.5 degree angle. Okay. So we have two sp3 carbons, and what is the central what is the central atom hybridization?
SP3B1, I think.
Just for this carbon, it would be sp3, and for this carbon, what would it be? Okay, so an sp3. Same thing, yeah. Okay. So we have an sp3 and an sp3. Okay. Essentially, we've got two tetrahedral carbons coming together. What's the electron pair geometry? Okay, no lone pairs, no lone pairs. So tetrahedral. Okay, is this polar or non-polar? This would be polar. Okay, those three CLs are pulling. Okay, there's no way you can arrange it so that the CLs cancels with each other. So yeah, it's polar. Okay, let me draw this one a little better. So this is how you would draw that. Okay, this is one way you can draw that structure. CL3. Okay. Two tetrahedrons. Okay, this is called dash, and this is dash. Okay. Okay, this is probably a better depiction of that. Okay. This is, and there's more than one. There's more than one way to draw this. Those are called isomers, by the way, isomers. More than one structure. Okay, based on, I can put the CL here, I can put all three CLs here, I can put all three H's there, So all those different depictions are called isomers. I can put one H here, one H there, another H here. I can put them all different orientations. Okay, all those different representations, those are called isomers. All right, here's our last one. Okay, I3 minus. All right, what is iodine happy at? Okay, 7 times 3 is 21. And what does that minus sign mean? Okay, so we need to get 22 valence electrons around I3 minus. Okay, so how will we do that? All right, so we will have an I Okay, halogens, which iodine is a halogen, it's in group 7. Iodine is in group 7. They don't like to form double bonds. So I'll do I with an I with an I. Okay, let's fill in the electrons. We need 22. Okay, ready? Okay, ready? I3 minus. Okay, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22. Okay. That's what it would look like. Okay, so we have so what is this then? Okay, how many bonds and how many lone pairs on the central iodine?
2 bonds.
2 bonds and how many lone pairs?
2. 3 lone pairs.
Very good. 2 bonds, 3 lone pairs. Okay, 2 bonds, 3 lone pairs. So what's 2 bonds and 3 lone pairs? Okay, so a total of 5. Out of those 5, 3 are lone pairs. So what is that?
Linear.
Very good. This is linear. Okay. Actually, it should be trigonal bipyramidal. Actually, it should be trigonal bipyramidal. But why is it linear? Okay, it's linear. Why?
Because it has the 3 lone pairs.
Because of the 3 lone pairs. Okay. It should be trigonal bipyramidal. That's the electron pair geometry. But because of the 3 lone pairs, 2 bonds and 3 lone pairs, this is linear. Okay. And how will we draw this linear? Okay, just follow this. I would just follow this. Okay, here's my I. I have one I going up, one I going down, 1 lone pair here, 1 lone pair at an angle, the other lone pair at an angle. Just follow this sheet. Okay. 1 eye going up, 1 eye going down. Okay, 1 lone pair straight to the left or to the right. Okay, a second lone pair at an angle. Okay, a third lone pair at an angle. And that would be what it looks like in 3D. Okay? It looks like a straight line. Okay, what is the central atom hybridization? 2 bonds, 3 lone pairs, total of 5. sp3d. Okay? sp3d hybridized iodine. And finally, is this polar or non-polar? All right, look at this here. This is going to pull at an angle. That's going to pull at an angle. What's the sum? The sum is to the right, which cancels out with which one, Jasmine? The left. Very good. Okay. So you are correct. This is not polar.